This is part 4 of the sequences and series topic. In this video we'll be focusing on geometric sequences. So these are the sequences where we're not going up by a constant amount each time in terms of addition, but rather we're multiplying each term by a constant. And we've seen some of these previously, but we haven't formally focused on them. So let's do that now. In a geometric sequence, each term is found by multiplying the previous term by a constant. This constant is called the common ratio r. So if we take any nth term and we divide it by the term before it, so Tn minus 1, this will give us the common ratio represented by r. And like we did previously when we were looking at arithmetic sequences, if we wanted to create a recurrence relation, we could rearrange this formula, multiplying both sides by Tn minus 1, and we see that any nth term is equal to r, the common ratio, times the previous term. Let's now look at the general term of a geometric sequence. And we will start just like we have previously, with our first term being equal to a. Then, when we look at our second term, following the geometric recurrence relation that we've just talked about, this is term 1 times the common ratio r. But term 1 is simply a. So we have a times r. Likewise, term 3 is the previous term, term 2, multiplied by the common ratio r. But we have just seen that term 2 can be represented by ar. And so when we tidy this up, we get ar squared. And let's just do one more to help us recognize the pattern. Term 4 is equal to term 3 times r. However, term 3 is ar squared, and when we multiply that by r, we get ar cubed. So whenever we are looking at any given n value, we can see that the power of r is 1 less. So here we have a times r to the 1, and even going back to term 1, there's like an r to the power of 0 here. So we can compare n with this power, n with this power. And we see each time that the power of r is 1 less than the n value. So generalizing this information gives us that the nth term is equal to a times r to the power of n minus 1. This power of r is 1 less than the term we are trying to find. And with that formula established, let's now have a go at some examples. We've got 4 that we're going to do in this video. Example 1, part A. Find x if 5x, 45, and so on is geometric. So if this is a geometric sequence, then we have a common ratio as we go from one term to the next. That means that the common ratio r is equal to any given term divided by the term before it. So t2 divided by t1 will give us the ratio, but we don't know x. However, because this ratio is common, the same can be said if we look at term 3, 45, and divide it by the term before it, term 2. So let's look at this equation now and substitute in what we know. Term 2 is x over term 1, which is 5. This must be equal to term 3, which is 45, over term 2, which is x. And so now we have an equation to solve where our unknown value is x. Let's multiply both sides by the denominators that we see. So when we do that, the x multiplies over to the left-hand side and gives us an x squared. And the 5 multiplies by the 45. And when we calculate that, that's 225. Now, taking the square root of both sides, we get x is equal to, now but square roots, remember we have to take the positive and the negative versions. We get the square root of 225. Calculating this, we find that x is equal to plus or minus 15. And both of these are actually acceptable answers for a geometric series. Let's have a look at part B of this question. Find the sequence. So previously we were given this, but in part A we figured out that x could be plus 15. So let's focus on that first. If x is positive 15, then our sequence becomes 5, 15, 45, and so on. And what can you see is the r value for this? What's the r value? Well, in this case, we have a common ratio of 3, right? And whether you notice that 5 times 3 is 15, or you ask yourself, what's 15 divided by 5? We can see our common ratio is 3. But remember, we also found that x could be negative 15. And I said this is okay for a geometric series. It would look like this. And in this case, what's our common ratio? Well, in this case, our common ratio is negative 3. And see how the sequence still makes sense. 5 times negative 3 gives us negative 15. But when we multiply that by negative 3 again, the two negatives make a positive, and we get positive 45. Okay, on to example 2. The third term of a geometric sequence is 18, and the seventh term is 1458. We need to find the first term and the common ratio. So let's start with the first bit of information that we're given, and that is concerning the third term, or T3, which is equal to 18. Now remember, we established that the nth term is equal to a times r to the power of n minus 1. So in this case, for term 3, where n equals 3, we have ar squared equal to 18. So this is our first equation. Using the second bit of information, term 7, we can do the same thing. So we also know that term 7 is equal to 1458, which means using this term formula that a multiplied by r to the power of 6 is equal to 1458. And so here is our second equation. So we have two equations and two unknowns, a and r. So let's solve them simultaneously. You might like to make a the subject of both equations and then set them equal to each other. That's perfectly acceptable. Or we could approach it like this. Let's take equation 2 and divide it by equation 1. So what happens when we do that? Well, on the left-hand side, we get a r to the 6 over a r squared, and that's equal to 1,458 divided by 18. And the nice thing here is that the a's cancel out. R to the 6 divided by r squared, well, that just becomes r to the power of 4. And when we calculate 1458 over 18, we get 81. To get r by itself, we need to undo the power of 4, so we're going to take the fourth root of 81. But just like square roots need a plus or minus out the front of them, so does any even root. So when we have an even power, like 2 or 4 in this case, or 6 and so on, when we take the root, we need to include a plus or minus. And so what answers do we get? When we calculate the fourth root of 81, we get 3. So r can be equal to plus or minus 3. So we've found our different values of r, but we need to find the value of a. Let's check what happens when we take the positive value of r. So r equals 3. And we're going to put this into one of our equations. Now, we could choose equation 1 or equation 2. Just going to go with equation 1. So we have ar squared, or a times 3 squared, is equal to 18. 3 squared is 9, so we have 9a equal to 18, and that leaves us with a equals 2. But we also had r equal to negative 3, so we need to check what happens there as well. So let's also sub r equals negative 3 into equation 1. And we can see because of the squared, that negative 3 all squared is just going to become 9. So once again, we get a equals 2. So whether or not we use r equals 3 or negative 3, the first term is the same, so that's a good thing. The first term is 2. And the common ratio could be either 3 or negative 3. And we're done for our second example. On to example 3. Is 1/4, 1/6, 1/18, and so on a geometric sequence? So in order to determine if this is a geometric sequence, we just need to see if the ratio is common as we move between terms. So let's first of all focus on term 2 over term 1. And that is 1/6 over 1/4. Now remember, when we're dealing with fractions over fractions, it can be nicer to use the divide symbol like this. And when we divide one fraction by another, we can do a times and flip of the second term. So we've got 1/6 times 4, so that's 4/6. Okay, so 4 over 6, but that can simplify to 2/3. So that appears to be the common ratio, but we just need to check if that's a consistent common ratio. So now let's look at term 3 divided by term 2, and that is 1/18, term 3, divided by 1/6, term 2. And once again, we will use the divide symbol instead, just to make things a little bit easier. When we times and flip, we get 6 over 1 when we flip our second fraction, so timesing them together gives us 6 over 18, and that simplifies to 1/3. So we can see that this r value is not the same. It's not actually a common ratio. So because we don't have a common ratio, okay, since we've shown that T2 on T1 is not equal to T3 on T2, then we don't have a geometric series. And that's how we would answer example 3. Okay, last example. Find the first value of n for which the terms of this sequence, 1/5, 1, 5, and so on, exceed 3,000. So we can see here we've got a starting value, so let's write that down. We've got an a value, that's 1/5. And hopefully you can see that the common ratio is 5, right? As we move from one term to the next, we're multiplying by 5. Remember, if you can't see that straight away in any given sequence, just do what we've done previously, one term divided by the term before it. And now that we have this written down, what are we trying to do in this question? What are we trying to answer? We want to know, when does a term exceed or become greater than 3,000? Okay, so what value of n gives us a term that is greater than 3,000? So how do we express Tn? Well, that's the formula a times r to the power of n minus 1. We want this to be greater than 3,000. And let's substitute in what we know. A is 1/5. Okay, so we got 1/5. R is 5. And then n is what we're trying to figure out. So we now have set up our inequality where the only thing we don't know is the value of n. So let's go about solving this inequality. Okay, first thing, that 1/5 there. Let's multiply both sides by 5 so that we just have 5 to the power of n minus 1 on the left. And on the right hand side, when we multiply 3,000 by 5, we get 15,000. Now, how are we going to get this n minus 1, which is up in the power, how are we going to get that by itself? Well, we're dealing with an exponential of base 5, so we are going to take the log of base 5 of both sides. So if we take log base 5 of the left-hand side, what that does, the log base 5 and the exponential base 5 cancel out to leave us with just n minus 1. Okay, but whatever we do to the left, we need to do to the right-hand side as well. So we have log base 5 of 15,000. However, log base 5 is not something that's particularly easy to calculate for us. We'd rather use a different base. So now is where we can use the change of base formula, okay, and we can choose whatever base we want, right, whether it's log base 10 or log base e. So it's up to you, right? Let's just use log base 10 in this example, which we can just call log. Okay, and the change of base formula tells us that we take this value here, it goes on the top, and our previous base, this value here, goes on the bottom. And remember, if you wanted, you could use log base e if you like to deal with the natural log, okay, but we'll just stick with log base 10. Okay, last thing to do is add the 1 to both sides. So we've got this value here which we'll calculate with the calculator, and then we'll add on 1. And when we do that, we get a decimal value of 6.974 and so on. So our n value, which has to be an integer, remember n values are, a natural number. Our n values are just counting numbers. Our n value has to be greater than this. So the next value that's greater than 6.974 is 7. So n is 7. That means that the seventh term, right, T7, that's going to be our first term to exceed 3,000. Now, this question didn't ask what that term actually is. It just said when's it going to happen. Okay, and so we have found our answer. And that concludes our video. Good work.